I want to take a look at some hand samples from the metamorphic outcrops here on the first stop of the trip, and talk a little bit about how you would look at these rocks in the field and very quickly come to the conclusion that they are indeed metamorphic rocks. They've been, you say, moderately metamorphosed. They're not right at the very onset of metamorphism, but they've not been extremely intensely metamorphosed. And we can also tell something about the protolith, about the parent material that underwent sufficient burial in the presence of the right fluids to be turned into the rock that you actually see here on the screen. And first and foremost, we're just looking at this, of course, on a photo viewer, but if you could hold this specimen in your hand and look at it closely, you would see that this sort of shiny gray-green material appears to consist of very small flakes of a gray-green mica, and that's the mineral chlorite. Chlorite is sort of by definition a metamorphic mineral. It crystallizes under metamorphic conditions in the presence of plenty of water. It's a very, very hydrous mineral. It's about 12% water by weight. And to have this much chlorite in a rock, you actually might call this potentially a chlorite schist. There's going to be a lot of water necessary within the parent rock mass to be incorporated into the chlorite structure as chlorite grows. In addition to the chlorite, you have these elongated sort of dark green minerals. These are an amphibole. It's probably actinolite or ferroactinolite. Combined with the presence of chlorite, this is also frequently a metamorphic mineral. You can say almost exclusively, but I wouldn't quite go that far. But taken with the presence of this amount of chlorite, add in some amphibole crystals as well, you know that this is a metamorphic rock because the chemistry of the materials present, along with their formative conditions, is really something that's only going to occur when existing materials undergo sufficient burial in the presence of an appropriate amount of fluid, in this case water. There's not a magma chemistry within the Earth system that can crystallize this mineral assemblage, so you can rule out an igneous origin for this material, at least in the form that you see it here, and we'll come back to that in a moment. And these are not very survivable minerals as well. They don't do particularly well with transport. They don't resist weathering particularly well, so producing a detrital sedimentary rock with this mineral content and texture is also impossible. So not only do the minerals themselves tell you it's metamorphic, it really can't be anything else. And certainly this is a fairly typical rock type to see in the part of the metamorphic Appalachians we call the Blue Ridge. Within this area, you expect materials to have been buried at least or over 15 kilometers, but probably not too much over that. This is sort of a moderately metamorphosed rock. You might say the uppermost green schist facies. Maybe in some parts of this area, rock might be approaching the Amphibolite facies, but this material could occur within a wide range of conditions because chlorite has a pretty wide stability range. Particularly in a rock with the right composition, it would be necessary to start with a basaltic composition to produce this rock, but specifically it would have to be a very magnesium-rich and silica-poor basalt. But with that starting composition, it's tough to break the chlorite down with increasing metamorphic grade, and you could see this mineral assemblage existing through a pretty broad range of conditions. Now, occurring along with this material in the outcrop is what you see here. This is the darker rock that is dominated by a darker amphibole that's probably hornblende or a calcic amphibole that's approaching hornblende's composition, and there's a lot of it. You would certainly call this rock an amphibolite because it's dominated by amphibole. And to produce a rock that contains this massive amount of hornblende-like amphibole, you would again need sort of a more typical basaltic rock starting composition. If you were to actually take a standard mid-ocean ridge basalt, what we call a MORB, acronym for mid-ocean ridge basalt, and metamorphose that at approximately the onset of amphibolite facies, you would end up with a very, very hornblende rich rock like you see here. So it's certainly not inconsistent with the chlorite schist that's occurring in the same outcrop on the roadside. It just requires a slightly different starting composition to produce this overall mineralogy. And tough to get a very exciting photo of this stuff, but if you look at it here with the light on it, you can see what appear to be sort of light colored needles here. That's actually just light reflecting off the elongated amphibole crystals. Most amphiboles are elongated in their habit. These are a little bit sort of stubbier, I guess, than the very elongated actinolites in the chlorite schist sample. But these rocks are, despite being different looking, they're actually not terribly different in terms of their probable origin, and of course their metamorphic grade is consistent between them. Now, how could you end up with this scenario happening? How could you produce this rock right next to this rock in the same outcrop and have them end up looking pretty differently? You have to think then about the probable setting in which these materials were located prior to metamorphism. A good way to sort of put together a tectonic story is to say that the rock we just looked at started its life as sills, or thin intrusive bodies, within the deeper parts of this sediment pile. Specifically, they would have been mafic sills of basaltic composition. If they were thick enough and cooled slowly enough to undergo some sort of fractional crystallization or evolution of the magma, a more magnesium-rich and silica-poor material could have crystallized initially from the melts, leaving behind a more evolved melt, so that initial material that crystallized would have been the parent material of the chlorite schist. The more evolved material that has a bit different bulk composition to play with, there's going to be a little bit more relative calcium, a little bit more relative silica, a little bit more relative sodium, and so on. That's going to crystallize into the amphibolite you see here. So intruding sills into these deep sediment layers here, metamorphosing those during tectonic thickening, and internally deforming those materials as well, such that they produce a very complex fold pattern and outcrop. And right next to these sills you would expect to find metamorphosed sedimentary material. And indeed, if you travel just a few hundred yards from this outcrop, you find very aluminous schists that are dominated by white mica, biotite, and some garnet, and that's the result of metamorphosing that more aluminous sediment. So right off the bat, whenever you see either of these materials, you know based on mineralogy as well as this foliated texture that they're metamorphic. You can then use that mineralogy to determine a protolith, and by putting that protolith into a tectonic context and comparing it to other materials around it, you can sort of make sense of why you see these rocks and their neighbors in this part of the metamorphic Appalachians that would relate to this part of our basic conceptual model.